In this video, we're going to present a short review of modern physics. In particular, we're going to cover 4 experiments: blackbody radiation, photoelectric effect, Compton scattering, and finally the Davison-Germer experiment. These were experiments which were fundamental in the development of quantum mechanics. So for blackbody radiation, the spectrum of a black body depends on the temperature of the object. For 5,000 Kelvin, you see the curve on the right here has a peak at about 0.5 microns in wavelength. As the temperature changes, the wavelength changes as well, and it scales inversely with temperature in such a way that you can see as you go to 4,000 Kelvin, then 3,000 Kelvin, the wavelength is longer. In fact, if you multiply the temperature times the wavelength, you get an invariant. And that invariant is lambda m, the maximum peak wavelength, times temperature is equal to 2.9898 times 10 to the minus 3 meter Kelvin cubed. So what you can do is if you scale the temperature, the actual or the wavelength to the maximum wavelength, what happens is that you get a universal curve. So all these curves will then lie on top of each other. The problem at the early part of the 20th century was that the classical theoretical model of a black body was unable to describe the low wavelength cutoff that was observed. In particular, the Rayleigh-Jeans model, shown in black here at 5,000 Kelvin, had what is the so-called ultraviolet catastrophe. And this results from the fact that the energy density of the electric field, U of lambda, is a function of wavelength, goes like lambda to the minus 4. And so this has a pole at 0. And as you approach 0 wavelength, shorter and shorter wavelengths, this explodes and goes to infinity. So how was this solved? Well, Planck's solution was to consider a metallic cavity that forced the electric field of the light waves to be 0 at the inside surfaces. Let's take a look at a simple diagram of that. Imagine a box, a square box like this. The edges are metal, and therefore the electric field at the boundaries has to be 0. Now, in order to have any kind of standing wave in this box along this length, then you must have an even number or a half even number of wavelengths. And so it turns out that the only modes that are supported in this cavity are the modes where the box dimension is a multiple of the wavelength, some integer multiple of the wavelength. Well, this is the postulate that Planck had. He postulated that there was a quantization of the modes of oscillation in the black body cavity. And the quantization looked like this, that the energy of a particular mode was the energy h nu times m. So m being 1, 1, 2, 3, and so on. And this means that the wavelength is a multiple of the base wavelength, which is the width of this box. So once you have this quantization of modes, you have an infinite but discrete set of modes. Each of the modes can be populated by quanta. And these quanta, the idea was that they followed the Boltzmann law, so that they were populated according to the temperature. That is, the higher the energy, the fewer states there were. When you take a black box like this, a black body, and you use Boltzmann's law and do a sum of all the potential modes, it's an infinite sum, you get that the field, the energy density, or the energy distribution as a function of the wavelength, has a very different form than just lambda to the minus 4. In fact, it looks like this. Its U of lambda is proportional to lambda to the minus 5 divided by E times hc over lambda kt. And this, of course, is a Boltzmann factor, minus 1. Now, as the wavelength goes towards 0, this Boltzmann factor does not go to infinity, because as lambda goes to 0, this cuts off properly. And the reason that happens is that when lambda goes to 0, you can ignore this term, and now U in the limit of lambda goes to 0 is e to the minus hc over lambda kt divided by lambda to the fifth. And while this is a large exponent, this is a large power law, the exponential drops off much more rapidly than even a large power law like lambda to the fifth. And consequently, this goes to 0. And this gives you the cutoff. So what this says is the quantization of the modes inside the box leads to a solution of the black body problem. The next experiment was the photoelectric effect. So in the photoelectric effect, you have a bare metal surface which is exposed to light whose energy is absorbed. That energy absorbing kicks out photoelectrons, and you can measure the kinetic energy of the photoelectrons by applying a negative potential and measuring when the current stops. Because when the current stops, you've reached the maximum kinetic energy that the electrons have coming out of the surface. Of course, there's a distribution of kinetic energy, as it turns out. Now, the electron emission in this experiment is found to depend on the color of the incident light rather than the intensity. For long wavelengths, for example, 700 nanometers, 1.77 eV is the quantized energy of this, according to Planck's constant. You get no electrons out of the surface. As you increase the energy and reduce the wavelength, so 550 nanometers and 2.25 eV, you now get electrons coming out, and you see that the electrons have a particular maximum velocity, which in this case we say is 2.96 times 10 to the fifth meters per second. So no electrons, then electrons with a certain maximum velocity. You reduce it even further, and to 400 nanometers and 3.1 eV of energy per quantized quanta of light, you get a maximum velocity of 6.2 times 10 to the fifth meters per second. So as there's more energy in the light, you get a higher velocity. Well, Einstein in 1905, and got a Nobel Prize for this, explained this by reasoning that light must be quantized according to its frequency. So very similar to what Planck had found out. And therefore, light has this particle nature. So the threshold wavelength of where you can start to get electron emission must be directly related to some energy. And this energy is called the work function. It's called phi of the metal. So the threshold frequency is equal to phi divided by h, because h nu is equal to an energy, and this is also an energy. From this, you realize that the maximum electron velocity must be a function of the work function and the energy of the incident photons. If you assume that the energy of the incident photons is h nu, where nu is the frequency of the light, then you have that h nu minus phi, which is the excess energy that the photon has beyond the threshold required to emit a photoelectron, must be related to the total kinetic energy of the electron. So it's equal to 1/2 mv max squared. So the intensity of the light, not the energy of the photon, determines how many electrons are emitted. The third experiment was the Compton scattering experiment. So this is a little bit later. In 1923, Arthur Compton measured the scattering of X-rays from a carbon foil as a function of exit angle, using a single crystal as an energy analyzer to measure the X-ray spectrum. So here we have the experimental situation. You have X-ray emission from a tube, a molybdenum tube. So the energy of that, the wavelength is 0.0709 nanometers. And it goes through you send it through a carbon target. Then you have slits, a calcite crystal which serves as an analyzer, a wavelength analyzer, and then an ionization chamber which measures the intensity of the X-rays coming through at different wavelengths. And so you keep the slit at 0, you rotate this around and rotate the detector around, and you get a peak that is centered around the incident X-ray wavelength, which is 0.709. Now, as you move the exit angle to a different angle, like 45 degrees, so you move the slit over here and the whole detector assembly over there, you start to see something different. You start to see some X-rays coming with a peak that appears to be growing at a longer wavelength. In this case, the peak wavelength is lambda prime is equal to 0.0715 nanometers instead of the 0.0709. And you still see the peak directly from the incident X-rays as well. As you go further out, the peak grows and it becomes more distinct. At 90 degrees, you really see two peaks and the wavelength gets longer and longer. And when you go to something that's close to backscattering at 135 degrees, now the peak is fully developed. You now see two peaks, one at the incident energy of the photons, and then the other at this new peak is at a wavelength at 0.0749. So the idea is, how do you explain this particular behavior of the X-rays that are scattered? Well, this can be explained using by treating the X-rays as particles, just like Einstein said, that interact with the electrons in the carbon atoms of the foil with an inelastic collision. So the peak wavelength of the Compton scattering can be calculated by applying relativistic scattering theory, which I will do briefly just so you can see how it works. So let's imagine we have a Compton scattering event where you have a photon-electron collision. It's an inelastic scattering event. So the incident photon has one wavelength, the exiting photon has a different wavelength, lambda prime. We don't worry about the elastic ones where it's the same energy. We're not interested in that right now. The incident photon strikes an electron. It collides inelastically. It leaves with a different energy, different wavelength, and the electron, which was initially at rest, moves off with a velocity v and at an angle theta, and you're measuring the photons that are coming out at an angle phi. Now, the momentum of the incident photon, p, is a vector. Right now, of course, it's a vector, and its magnitude is 2 pi h bar over lambda, and its energy is hc over lambda. The exiting photon at the angle phi has a momentum p prime, whose magnitude is 2 pi h bar over lambda prime. This is an inelastic process, and therefore the wave number, the wave vector of the incident electron is not equal to the wave vector of the exiting electron. Not only is it not in the same direction, but its magnitude is different because it's an inelastic process. It loses momentum, changes momentum, and loses because some of the momentum is given to the electron. What we have to do is treat the electron relativistically, and we want to conserve energy and momentum both. So for the energy conservation law, we have mc squared, which is the rest energy of the electron, which is not moving initially. And we have hc over lambda being the energy of the incident photon. That's on the left side. On the right side, we have hc over lambda prime, the energy of the exiting photon, and gamma mc squared, which is the energy of the electron moving away at a velocity v. And this we treat relativistically, so we use the gamma factor. For the momentum, we have in the x direction, we have initially h over lambda, and then nothing from the electron. And then after the collision, you have h over lambda prime cosine phi. And then you have the momentum of the electron in the x direction, which is gamma mv, that's the momentum, relativistic momentum, times the cosine of theta, which is this component of the velocity of the momentum. And in the y direction, you have no momentum initially because the incident photon's coming in along the x-axis, and then you have on the after the collision, you have h over lambda prime sine of phi for this component of the momentum of the photon, and gamma mv sine of theta for this component of the momentum of the electron. And these must all be used to eliminate the two things that we don't care about, which is the velocity of the electron and the angle of the electron. What we're interested in is finding out what lambda prime is for a given value of phi. So we do this by squaring the momentum equation. So the first thing we do is we take the term that belonged to this side and bring it over to the side with the photons. So we keep all the photons together, and we have h over lambda minus h over lambda prime cosine phi, quantity squared, is equal to gamma squared m squared v squared cosine squared of theta. That's the x direction. And in the y direction, again, we bring the photons to the left side, and we have minus h over lambda prime, sine of phi quantity squared is equal to lambda squared m squared v squared sine squared of theta. Well, clearly, if we add these two together, we'll get something on the side of the electron that has the same prefactor, and then a term that looks like cosine squared plus sine squared, which is equal to 1. And so we add them together, we get the following. Gamma squared m squared v squared times the quantity sine squared theta plus cosine squared theta is equal to the stuff in brackets here squared plus the stuff in this bracket here squared. Now this goes to 1, and then we want to expand these two terms. So when we expand that, we get on the left side gamma squared m squared v squared is equal to, and now from the blue bracket, blue parentheses, we get h squared over lambda squared minus 2h squared over lambda lambda prime cosine phi, and then plus h squared over lambda prime squared cosine squared of phi. And from the red one, we get h squared over lambda prime squared sine squared of phi. Again, we can factor out the common first term here, and we get sine squared phi plus cosine squared phi. And that goes to 1. On the left side, we're going to replace gamma with its value, which depends on the factor beta, beta being v over c, where c is the speed of light. So if you recall, gamma is equal to 1 over the square root of 1 minus beta squared. So gamma squared just gives you a 1 minus beta squared in the denominator. In the numerator, you have m squared v squared. On the right side, we've canceled out the sine squared plus cosine squared, and we get h squared over lambda squared minus 2h squared over lambda lambda prime cosine phi plus h squared over lambda prime squared. Now, one more thing, we realize that beta and v have a relationship, that is, that v is equal to beta times c. So if I replace the v with beta, I get m squared c squared beta squared over 1 minus beta squared. So we'll now remember this, and we have a third equation that we can deal with, and that is the energy equation. So we're going to do the same thing with the energy equation. We bring the photon, the exiting photon momentum over to the left side, and so we have the rest energy of the electron, mc squared plus hc over lambda minus hc over lambda prime quantity squared, so we square everything. And on the right side, we can get, again, gamma squared m squared c to the 4th. Now, again, we can replace gamma squared by 1 over 1 minus beta squared, and we can now solve for beta. So if we solve for beta, we get the beta squared is equal to 1 minus m squared c to the 4th over mc squared plus hc over lambda minus hc over lambda prime, all quantity squared. If we take this and put it into the terms of the momentum equations, remember we had a beta squared on the top and a 1 minus beta squared on the bottom. Well, the beta squared is just this, and the 1 minus beta squared, you can see immediately from here that that's just equal to the second term. So that gives you a 1 minus beta squared, that gives you this term on the top and this term on the bottom. And over here, you get two terms. You get 1 minus this term here. So when you put those in and cancel them out, cancel everything out, it becomes a relatively simple expression. You get a 1 over c squared, mc squared, plus hc over lambda minus hc over lambda prime quantity squared, minus m squared c squared. And this now can be further reduced. The first thing we want to do is now expand this term here, the squared term. And if we do that, we get m squared c squared, h squared over lambda squared from this term, h squared over lambda prime squared from this term, and then you have the three cross terms. You have 2mch over lambda minus 2mch over lambda prime plus 2h squared over lambda lambda prime, and then you have a minus m squared c squared. So the first thing you notice is that this term and this term will cancel. And so we're left with, now if we gather these two terms and take out the common 2m factor, we're left with 2m times the quantity hc over lambda minus hc over lambda prime. And then we have these three terms, h squared over lambda squared, h squared over lambda prime squared, minus 2h squared over lambda lambda prime. And now if you look on the left side, you see that this term cancels this term cancels this term, and then these two are common terms. So we can cancel these terms. This prefactor appears on this side, so if we bring this over to the right, we get this quantity times 1 minus cosine theta. On the right side, we have left this term here. And so we're left with this, where you have 2h squared over lambda lambda prime times 1 minus cosine phi equals 2m hc over lambda minus hc over lambda prime. And these, of course, are energies. Now, if I pull out the hc, I get 2mhc, and then I put these over a common denominator, I get lambda prime minus lambda over lambda lambda prime. And you'll notice that this denominator is the same as this denominator. They're going to cancel out. And so when I do that, I realize also that lambda prime minus lambda is merely the change in the wavelength, delta lambda. So this becomes 2mhc delta lambda over lambda lambda prime. When I cancel out the lambda lambda primes in the basement, I get my final, and I cancel out some of the other constants, the 2 and one of the h's, I get that I have delta lambda. When I solve for delta lambda, I get delta lambda is equal to h over mc times 1 minus cosine phi. And that's exactly the result that we want. If we now look back at this data, that we have the Compton effect, and we realize that delta lambda is equal to h over mc times 1 minus cosine phi, you can explain the appearance of the second peak. At the angle 0, this is equal to 1. And so this cancels, and you get no delta lambda is equal to 0. So the two peaks sit on top of each other. As if you go to 90 degrees, then cosine of phi is 0. And so you get delta lambda is equal to h over mc. When you go to 180 degrees, that is backscattering, then cosine phi is minus 1, and you get 2h over mc. And that is the biggest distance that you get between the two wavelengths. So this explains the energy change of the broader peak with increasing angle. Now, you can also explain the width of this peak, because this is much narrower than this one here, and the reason is that we made an assumption that the initial electron was at rest, and that's certainly not the case in general. The electrons are in a solid, they have some velocity, the velocity can be in any direction, and so that will give you slight variation in the final wavelength. Depending on the initial velocity of the electron, it's a much more complicated thing to calculate. And that's why the Compton peak is so broad. The electrons are not really stationary, and there's a spread of energy and momentum in the outgoing photon. The final experiment that we'll talk about is the Davison-Germer experiment. So this was presented or published in 1928. Davison and Germer measured the peaks in the reflectivity of electrons from a single crystal of nickel. So this is a little bit different. So far, we've talked about photons having particle-like nature. These are particles that turn out to have a wave-like nature. So the experiment is as follows. You take electrons from a source, accelerate them to varying potentials. So you change the potential, the accelerating potential. That means you change their kinetic energy. And then you let them be incident on a single crystal of a nickel surface, a single nickel single crystal surface at a fixed angle. You then put a detector at 2 times that angle, and watch at the change of intensity as you change the energy of the electrons. So what happens there is you see these regularly spaced peaks, but the regularly spaced peaks are regular in terms of the square root of the accelerating potential. So they occur at regular intervals in V accelerated square root of the accelerating potential, and they correspond to Bragg reflections of the electrons from the nickel 1,1 lattice planes. That is very much like the Bragg reflection that you see for X-rays. That is, they behave with this law, 2d sine theta equals n lambda. Now, what is lambda? That means that the electrons must have a wavelength. And from this, you can go back to what had been done by Louis de Broglie, where he hypothesized that there was a wave nature of particles. And so this was an experiment which demonstrated that de Broglie's postulate was correct. Now, what did he say? Well, he said that the momentum of an electron, of a particle, is equal to Planck's constant divided by its wavelength. This is an analogy with a photon. And therefore, 1 over the wavelength is equal to the momentum of the particle divided by Planck's constant. Now, what this means, 1 over the wavelength is proportional to the frequency. And so what that means is that as the momentum rises, the frequency rises and the wavelength gets smaller. So the higher energy the particle, the shorter the wavelength. You can then rewrite this Bragg's law, which was what was found by this experiment. Bragg's law can be rewritten as 1 over lambda is equal to n over 2d sine theta. And 1 over lambda is related to the momentum over h. But the momentum, in classical terms for a non-relativistic electron, is equal to the square root of 2m times e, the charge of the electron, times the accelerating potential. And this explains why, when you plot versus the square root of the accelerating potential, you get evenly spaced lines that are multiples of 1 over 2d sine theta. And you have this this integer here that goes from 1 to infinity, or 1 to 6 in this case. So this could only be explained by the interference between electrons and themselves, and it proves the wave nature of these particles. So the Davidson-Germer experiment was published in the Proceedings of the National Academy of Sciences in 1928. And the historical account of this discovery was interesting. It's an interesting read. It was published in 1978 in Physics Today, and it's available. You can find it online easily from the American Physical Society. Now, that's the end of this short review. And what we've learned here is that waves, like photons, light, can behave like particles, but particles can also behave like waves. And this leads us to the conclusion that we have to have a wave equation to study and to understand how particles move when we're really talking about individual particles.